remind everybody to please mute your cell phones, which I just did. Before I introduce tonight's speaker, I want to mention that this coming Friday, 6 of us will be teaching 10 classes, 240 students at Jackson Hole Middle School about Yellowstone, one of the other volcanoes. And this is a good chance for anyone who would like to observe a class being taught to see if it's something you might want to do at some point. If you're interested, talk to me tonight or email me and we can get you the time and the place and everything else. Our speaker tonight is Doug Owen. Doug has a Bachelor of Science degree in both geology and education from Kent State University. He taught earth science for 8 years in Ohio, then went to work for the USGS doing research. He worked for them for 16 years. He left that part of the Department of Interior and went to work for the National Park Service, where he was the lead interpreter and park geologist at Craters of the Moon National Monument for 19 years, is that correct?
Yep.
For 19 years. While at Craters, Doug wrote Teacher's Guides, the Geology Guide, which is on the table there, site bulletins and maps. If I were to list all the awards and conferences where Doug presented, he wouldn't have a chance to talk tonight. So I'm going to skip that since you're here to listen to him. In short, I don't think there's anyone more qualified to give a presentation on the Snake River Plain and Craters of the Moon National Monument. Please join me in welcoming tonight's speaker.
I'm representing the Craters of the Moon Natural History Association tonight. I'm one of the board of directors. And one way that you could help us out would be to potentially purchase some items from them. And I brought 2 that are related to the geology if you wanted to dig into it more or plan your own field trip. One is the Geology Guide that you can come up here to the table and take a look at that we have available. The other is the geologic map. I work with what we call GIPs or geoscientists in the park, used to be geologists in the park, in conjunction with the Geological Society of America. Most years I had 2 GIPs working with me. We did a lot of mapping at 1 to 12,000. And kind of the high visitation area got compiled into this map that's you can see here if you come up and look at it later. And we also took some of the prime geologic features we call points of geologic interest that are yellow circles on the front. They have also the GPS coordinates. And so if you wanted to plan your own field trip to see some of these key geologic features, this is a good tool. There's an order form here on the desk you can take a picture of with your cell phone when the program's over. And it's got the phone number, which is probably the easiest, back to the Natural History Association. So if you want more depth than what I go into tonight for either one of these products, then you can contact the Natural History Association and order them. So that's kind of a plug for the group that sent me here. Okay. We're going to be taking a look at the geology of Craters of the Moon and the Eastern Snake River Plain, which extends all the way, of course, up to Yellowstone. So the monument is that area inside that heavy black line, the Craters of the Moon lava field. Covers about 618 square miles or 1,600 square kilometers. And it is the largest geologically young, dominantly Holocene lava field in the lower 48 states. Like was mentioned at the start, you're going to have to go to either Alaska or Hawaii if you're going to see so many basaltic features as you can see in Craters. There are some older things. That's not what I wanted to do. Back to the beginning. There we go. Hot button's the laser. This little guy right here, or over there, that little guy right there, is Laidlaw Butte. That is also volcanic. It's actually a shield volcano. It is the largest volcano in the Craters of the Moon National Monument and Preserve, but it's much, much older. It's about 425,000 years old. That's about 900 feet of vertical relief on it. So there's older things out there. There's also other young things like the Wapai lava field, and some of you, I guess, went to Kings Bowl right there a few weeks ago.
Yep.
And those are about 2,200 years old. So there's a couple other young ones within the park. Kings Bowl, one of the reasons why the monument is extended clear down there, has some of the deepest open volcanic rift on a landmass. Humans have actually descended in the volcanic rift more than 600 feet from the surface down there at Kings Bowl. Certainly there's way grander things out in the ocean. Some of the things there are thousands of feet that, you know, they've gone down in submersibles, etc. But on a landmass, Kings Bowl is pretty cool. Kind of comes down to two big picture items. One is the track of the Yellowstone Hotspot, which tracks from McDermott Field down here in Nevada on up to, you know, the most recent caldera event in Yellowstone, which is 120,000 years ago, West Thumb, which, by the way, happens to be a perfect analog for another park. Mount Mazama, when it blew at top, left a little puddle, kind of deep, about 2,000 feet, over there in Oregon. Crater Lake is a perfect analog to West Thumb in Yellowstone, which is the youngest caldera in the park. And they track up the Snake River Plain, getting progressively younger from about 17 million years ago on up to the 120,000 years ago caldera event in Yellowstone. The other big thing that's important, and certainly important to all you guys in the room, because I'm assuming you're from the area, is Basin and Range extension. You're kind of on the eastern edge of it, and we'll look at other slides of that. But that's a key factor too, because when you stretch the crust apart, if there's any hot rocks down there, they tend to become molten. It's called decompression melting. And of course, the track up the Snake River Plain is pretty equivalent to the Emperor Island chain and the Hawaiian Islands, you know, being tracked over a hot spot. The hotspot at this point has been imaged to over 1,000 kilometers in depth. This is a picture from Allen's that was in the Grand Challenges of Seismology. You can see Yellowstone and a hotspot extending way farther down than they originally thought the hotspot might do. They kind of had a two-stage theory there for a while, but it's definitely something that's quite deep. And if you go to is Bob Smith in the audience tonight by any chance? Nope. Can't get it directly from the horse's mouth then. But it's one of Bob's figures. He's a member of your group anyway. And he says that basically the best fit for the Yellowstone hotspot is to project it clear down to the core mantle boundary, which is kind of cool. So that's some of the big picture stuff. Another illustration from Bob, and this was from the Journal of Volcanology and Geothermal Research. And basically what he's saying here is this is where the hotspot actually kind of was starting up, but this is where it touched the surface. So you have to keep in mind there's a couple of big picture things going on here. One, this mantle plume wants to move up, but within the mantle there are convection cells. And so those mantle circulation wants to bend that plume over. And as it ends up, it gets bent over at an angle of about 60 degrees. But the other thing that happens is we have continental drift, and the North American plate is drifting off to the southwest. So the plume kind of wants to come up, it gets bent over, and the plate motion drags it. And so where it actually comes in contact with the crust is over here. As a result of that, there was an awful lot of material left in what's called the mid-crustal sill, about 10 kilometers or 6 miles of it. And that's kind of the source for all these basaltic eruptions that made it up to the surface, including creating craters of the moon. One estimate was that there's probably been about 8,000 basaltic events to pour out this basaltic frosting on the eastern Snake River Plain. Here's another idea too, and something that's still open to debate. There's different ideas out there. Did that hotspot come up in front of the old Farallon Plate, or did it come up beneath the old Farallon Plate? Well, this is one obviously where you're having it come up in front of the old Farallon Plate. This is a picture from, shoot, it's probably on there, Ken Pierce and Lisa Morgan. And so if it came up in front, the plate's going down, and you create a shear couple. So as this one's diving and this is coming up, you get to this kind of circulation pattern, and that tends to drag the material out. One thing you have to explain in geology is the whole regional scenario. And one thing is there's a track across the lava plains of Oregon over to Newberry Crater that gets progressively younger. And then you've got this other track that goes on up to Yellowstone. Well, this is one way to explain some of that, is it gets drugged there. But there's other alternatives too. This one is an idea where it came up beneath the Farallon Plate, kind of pooled, made a big plume head, and finally it breached that and also poured out a lot of lava. One of the big questions is, we have these what are called large igneous provinces in geology, things like the Deccan Traps, etc. Well, the Columbia River flood basalts are kind of significant. About 42,000 cubic miles of material got poured out. That's a fair amount of stuff. And having it kind of pool beneath the old plate and then breach it is a good explanation for it. But you can also go back, and if you have the plume head come up in front of it, you have to remember the only reason basalt wants to move to the surface, because it's a heavy, dark, black rock, it's kind of like gabbro down in the mantle, is that there has to be enough flotation or buoyancy to bring it up. It's kind of like a submarine. And one way to get this to come up to the surface then is to have it come up and then it says, oh, I'm hitting this old, oceanic material. And part of that is because over there near Boise, that used to be the edge of the continent. Everything else between basically the Boise area on off to the west coast is stuff that's been docked as these plates got consumed. And so if you have it come up and it hits this old oceanic material that's a similar density, until you have enough time for fractionation, which kind of means crystallize out things that have high temperatures before they become solid first, and then you can get, over time, it change more and more to lighter density material. And then you can have these big rhyolitic blows that poured out a lot of stuff, like over in the Huckleberry Ridge Tuff. It was like 600 cubic miles. Material blew out in one pop. So buoyancy is really, really important. And we looked at that one. So there's the mid-crustal sill, presumably kind of the source area for the magma chambers that brought stuff up to the plain. And over time then, a huge, huge volume. Just west of the park boundary, we now know the basalts are over 6,000 feet thick. Project Hotspot drilled down through over 6,100 feet of basalt and didn't get out of it. So some places, even the frosting on the surface up here is greater than a mile in thickness. A lot of dense materials. This has a profound effect for what the plane does, and the plane goes down. It's like you guys, Mike here likes to fish. He did tell me he likes to fish, as a matter of fact. And he goes out in his rowboat, and he invites a few friends with him. Well, the first person gets in, the boat sinks a little deeper. More people get in, it sinks a little deeper. Well, when you've got, 10 kilometers, 6 miles here in the midcrustal sill, and all of the stuff up there, it's like loading that boat. And so the plate is actively going down. And at the edge of the plain, that also has profound consequences as well. If you go to Arco and look at the edge of the mountain range, the Lost River Range, it dips down towards the plain. Some of the dips that have been measured by the geologists at ISU are as much as 30 degrees. So this loading by all this dense black rock, profound impacts to the edge of the plain, and then as you go back up, they flatten back out. So all that loading has other consequences to the geology. Well, what do these fractures, what we call the volcanic rifts, look like as opposed to faults? And here's the, shoot. I keep expecting the bottom button to be the laser, and that's the top button. So here's the Great Rift looking back towards Coyote Butte, Big Cinder Butte, out there on trench mortar flats in the park. Sometimes as this basalt's moving up, it kind of splays it apart. It's kind of like putting a chisel underneath something and causing it to split. Or if you split wood, putting in a chisel and trying to pull that log apart. It's the same kind of things as a dike or a blade of basalt tries to work its way to the surface. Other times, it has a fault expression. Here's, probably a good 10, 12 feet of fault offset. This is called Dick's Fissure. It's a continuation of the range front fault along the Lost River Range at Arco, extended out onto the plain. You don't see it in a lot of places. Most places that dike emplacement has filled in and absorbed that gap, and you don't see any offset. But there are places, like if you go into the eastern edge of the Craters of the Moon lava field, there's some fault scarps there that are also about 10 or 12 feet. This is down where some of you guys went a couple weeks ago, I guess. This is King's Bowl. That is the Great Rift right there. As you can see from the big steam explosion that took place and blew the rocks out to form the bowl at King's Bowl. So sometimes it can be pretty doggone impressive. This is a fault scarp near the visitor center. This is a GIP that worked for me named Tiffany. And as you can see, she's a little over 5 feet tall. That's a fair amount of offset. But that is at right angles to the Great Rift. It is due to the volcanism, but this represents a collapse back into the magma chamber. It's kind of like you pour a bunch of stuff out onto the surface. Mother Nature abhors a vacuum. Something's got to settle, something's got to give. And so sometimes you end up with faults like this from a collapse back into the magma chamber as well. There's the kind of diagram for Basin and Range Province, and you can see we're kind of over here at the eastern edge. And someday here at Baja, California, we'll decide, oh, Death Valley, 200 feet below sea level. I should fill that in. And of course, in the distant future, millions of years, as the stretching continues, someday, we're going to have a separation. This will be an inland sea, kind of like the Red Sea that's over there near the East Africa Rift. So that's a part of this big picture story too. If you look at the volcanic rifts on the plain, all these things here in blue, and then the mountain ranges, there seems to be at least a parallel to subparallel relationship between the volcanic rifts and the range front faults for the mountain ranges. You notice the big fluky thing is here at Craters of the Moon. What should be right there?
World fault.
There should be another valley running up there. There should be, just like you have here for the Lost River Range, there should be another big valley there. And perhaps the reason, we've had 25 major cones, 8 eruptive periods, 60 lava flows in the Craters of the Moon field is because the extension is having a heck of a time marching up here into the Pioneer Mountains. And so a lot of that relief took place along the Great Rift, pouring all these flows out, whereas many of the other things out there seem to be kind of one event, it happens, and then it goes someplace else. Basin Range Extension is alive and well in Idaho. It is over here too. It's just been sleeping over here in Wyoming for a while. This happened back in 1983. Originally it was classed as a 7.3. USGS downgraded it to a 6.9, but still a significant event. This is the highest peak in Idaho, Mount Borah. It went up about 1 foot as a result of this event. And here you can see the step-like or an echelon faulting as it stepped down. Some books say as much as 16 to 21 feet for maximum offset. Average was somewhere between about 7 and 9 feet. And most of that offset was the block that's the valley bottom that dropped. And Borah Peak only went up about a foot. With most basin range extension, the down drop part, the graben, is more significant than the uplifted part of the mountain ranges. But this just happened, 30 some years ago. So the Borah Peak quake says, not done yet. Seth Carpenter, he's working for the Geological Survey of Kentucky now, but he worked out on the INL. And basically this is saying there's been some occasional activity both at kind of the mantle crust boundary and also up at the mid-crustal level that vaguely hints like, something may be going to happen again here. Other than that, we got to try and stay on time, and this can be a 2-hour talk, and you don't have 2 hours, so we're going to have to rush. Anyways, back to buoyancy. Yes, this basalt wants to move up. It tends to come up as a dike or a blade. It tends to splay the surface open, and if it makes it to the surface, then you have an eruption, like here we call eruptive fissure. You also get, based on the physics, this kind of zone of tension, and you tend to get non-eruptive fissures on either flanks to the erupting part. Most of the time, those get buried by the lava flow, and you don't get to see them. But occasionally you do. So here's a view down at Kings Bowl, where some of you were a couple weeks ago. And lo and behold, you can see at Kings Bowl, did you guys go out to see the non-eruptive fissures?
No, we did not.
You did not. They're really cool, and they're better seen actually from the air anyway. But these are the non-eruptive fissures. If this flow had been more extensive, it would have buried these and you wouldn't have got to see them. So there's the bowl. You guys did go down in the bowl, Mike told me. And here you can see the little plume of ash. So when this blew out as a big steam explosion, the ash was lighter and it got carried off to the east. And a lot of the blocks and stuff you guys were looking at were over in this kind of, if you will, lava lake, lava pond, and you got all those kind of really cool squeeze ups to it. The deepest part of the Great Rift is actually down here near an area that's a bunch of spatter cones called South Grotto. And that's where they actually descended 600 feet from the surface in the volcanic rift itself.
Did they hit the bottom?
Well, some of the blade is still down in there, but that's how far they were able to get. The guy that went down in that, I talked to him, is one of the grottos, and he said he would never ever do that again because he could hear these rocks whizzing by his head because the floors in there are perched, they're rubble and ice, and as they melt and change and collapse, it's just an incredibly perilous thing to do. And even for spelunkers, which tend to be a pretty brave lot, it's like, life is too precious. I'm never going to do that again. Once you have an eruption taking place, You tend to start off with kind of a curtain of fire, and then as it gets choked or clogged, it tends to center down to one or a few vents. And when that happens, then you can get this really high fountaining. This is the Pu'u'o'o vent down there in Hawaii. And the cone here, this is probably quite similar to this. This is Big Cinder in the park. You can get very close to that within about a quarter mile on the driving loop. And this has got between 700 and 800 feet of vertical relief on it. And it's kind of the fallout pile like you're seeing over here. So the fountain that produced this guy was actually probably quite similar to that. So one of the kind of cool things easily seen in the park. The Great Rift has many different expressions. It has, kind of the crack, okay, that's pretty easy. People up there for scale, King's Bowl again, the Great Rift right in there. But sometimes, here's the rift that was erupting. We talked about it being kind of choked or clogged and centering down to one or a few vents. Well, this was definitely several vents right in here. Sheeptail Butte. And sometimes, you see it like this with a series of little spatter cones. Other times you do get a little bit of a graben-like affair off to either side. And this is part of the trench mortar flat event, and it goes back to this flow here, which is a flank eruption on Watchman Cone. And there's another flank eruption on the other side of Watchman. But this extended for several miles. Same place, trench mortar flat looking back towards Big Cinder. Sometimes you'll get a Spatter, so here's a eruptive vent, here's an eruptive vent, eruptive vent, eruptive vent. So sometimes they can be a little bit subtle. So there's many different appearances to some of these eruptions as well. The oldest one in the craters of the Moon lava field itself is Crescent Butte, roughly about 15,000 years old. The biggest one in the craters of the Moon field is Big Cinder, between 700 and 800 feet high. Not the biggest volcano in the park, that's Laidlaw. And here's a close-up of that flank eruption, and there's one on the opposite side of Watchman too. This one we think was roughly 13,000 years old, and then got reactivated with the trench mortar flat event, which was 2,200 years ago. Spatter cones and hornitos are cool basaltic features that you get in the park. Spatter cones are made out of globs that got ejected, probably no more than max, probably 200 feet in the air, fell back around, made these really steep little sided cones. They're what are known as rooted vents. They have a direct connection to the eruptive fissure itself, in this case the Great Rift. And then we also get things like these guys, these two, which look very similar, but they're known as hornitos. In Spanish it means little oven. And hornitos are rootless vents. They are not fed directly by the eruptive fissure, but are actually fed by lava tubes. So a hole in the lava tube, gases and stuff, spatters the stuff or oozes it out, makes these similar steep-sided little cones. So depending on the origin, it's either a spatter cone or it's a hornito. Also, you get spatter ramparts. Rampart, Great Rift went through the middle. Stuff gets thrown out, lands on either side, and builds up these little low ridges, which are called the spatter ramparts. So here's a rampart, people, for scale, and then more of a spatter cone down there with a kind of an arch to it. Kinds of lava. We have several kinds of pohoihoi, and we also have a'a. The two basic kinds of a'a are the classic giant crumbled cookies. It's kind of like, Paul Bunyan told, "Hey, Blue, eat these cookies, they're good for you, give you energy." And Blue says, I want alfalfa. And so all the Oreo cookies got left behind. So that's giant crumbled cookies. Big blocks of chunky stuff. Geologists actually gave it a name that makes sense. block lava, because it looks like blocks. So these are the two basic kinds of this is kind of a subset of aha. In the more fluid lava, we have what's called shelly pohoihoi, and it tends to form only real near the vent, the eruptive fissure, or near a skylight in a lava tube where it's been insulated by the roof of the lava tube so it didn't cool off quickly. And then you tend to get all these little open blisters. And so this is just a classic shelly pohoihoi, and you can see your feet underneath, so you can see it forms shells. If you go to some place like Pillar Butte area out on the Wapai lava field, the shells are so thin there because you're near the vent area, you have to watch you don't break through and slice your shins open. So shelly pohoihoi, pohoihoi in general, this is what it takes its name from, because that means ropey in the Hawaiian language. And geologists went to Hawaii to see the stuff forming, and so they adopted many of the Hawaiian terms. If you have lava that's rather thick, still pohoihoi, but gas bubbles and things, it's kind of like doing a Mother Nature's taffy pull of the liquid rock, then you end up with spiny pohoihoi. If you feel this with your hand, you see these little spines or ridges to it. And that's the most common type of lava in craters of the moon, is spiny pohoihoi. Another type you get are these things here. You can see this kind of a big slab. And so if the gradient is steep enough and the lava says, oh my goodness, I'm feeling the stress, and that surface crust gets kind of churned up, it's like Mike here again. He's going to run the Snake River. Well, you know, if he's in a nice gentle gradient area in his raft, what does Mike got to do? Well, relax, but he's also got a paddle, right? Now he gets to the really whitewater section and he's hanging on for dear life. And in the case of the lava flows here, this is kind of like Mother Nature's taffy rapids. So as this congealing crust gets torn apart because the gradient increased or because the surface it's flowing over is so rough, there's a really high coefficient of friction, then it gets sheared up into all these slabs, and that's fairly common. And most of what the people look at in craters of the moon and the part that's developed, and they think it's actually slabby pohoihoi. You also get tachyllite, which is kind of a almost obsidian. It doesn't have the right chemistry to be true obsidian. It would have to be over 70% SiO2 or silica. Some of the stuff in the park, though, is up over 60. So technically, it's not a basalt. It's actually what they call a basaltic andesite. And where you find most of this stuff is actually in cinder cones, because this stuff got ejected as a froth, shocked when it landed, buried rather rapidly and compressed by the overburden, forcing the gas bubbles out. I'm an old fogey, if you couldn't tell, and I've never owned a dishwasher in my life. And so I do dishes in the sink. And before Dawn got invented and you had old-fashioned dish soap, you know, you'd have all this nice foam on your kitchen sink, and if you disturbed the foam, it went flat. That's how this stuff forms. And the Hawaiian geologists refer to that as the foam dispersal model. So shocking with the impact of landing and then getting buried quickly and compressed, forcing the gases out, you end up with these kind of banded glassy areas, particularly in some of the cinder cones. You also get some blue glass. There's still no definitive word, though NASA is actually working on this right now. And the one idea came from USGS about 30 years ago, and that was a little bit of titanium in the iron mineral magnetite they thought produced the blue. Some of the more modern ideas out there is that maybe more of a ceramic property, like a glaze you put on a pot and, you know, fire in a kiln. And if I had to pick one that my brain says it accepts quicker, it's probably the glaze idea rather than the little bit of titanium. But NASA is actually currently looking at that. Other kind of cool features, cooling cracks, alias dragon's teeth. So when you do tours, you have the little kids stick their leg down in the dragon's teeth and get their picture taken by their parents. But they're actually cooling cracks. You can see most of these are breaking out into four-sided polygons, which is fairly common to a number of the basalt flows here. But geologically, worldwide, the most common for cooling cracks is six-sided. So 6 is what nature tends to prefer. For some reason in craters, a lot of them are four-sided. We also get squeeze-ups. Here's a hiking stick for scale. And there used to be a big one over near the North Crater Flow Trail called the Devil's Sewer, which got loved to death by people and stolen and broken and no longer exists. But as you have a crack in the crust of a lava flow, and the stuff tends to get forced up by these expanding gases. Because you have to remember, if you're molten rock at depth, you know, you have maybe miles of overburden providing pressure. Fluids, liquids, gases are dissolved in that melt. It gets up near the surface and says, what? All I got above my head is this puny column of air? And so things that were happily dissolved at depth start coming out of solution. They exsolve. And then it takes some of the lava with it, and you get these billowings up that form sometimes these really cute pipes. Of course, the distal end of lava flows, just like the distal end of your feet, you get toes. And then some of you guys went and looked at these down at King's Bowl. This is one of those Hershey's Candy Kisses, Swiss Army knife for scale. When that steam explosion took place at King's Bowl, blew out the ejecta, and when some of that ejecta broke through the crust on this little lava pond, then the lava flowed up and made all these bizarre shapes like the Candy Kisses. But you can also have a flow ridge. So here was, in essence, a channel of lava, and you get a tension fracture at the top, because once it's solidified, it continues to expand, it has to crack. And if there's enough pressure internal, these gases coming out of solution, etc., forcing material up and out, they can flow down the edges. And so those two are considered as squeeze-ups. So another one of those nice features you can see in the park. Small domings. You can see how this is kind of domed. These are called tumulus or tumuli. And if you look at a tumulus, they often have a very prominent tension fracture. And often you can see all of this really cool vesiculation, which means layers of bubbles. And each one of those layers of bubbles represents a surge or a pulse of lava down through the tube. Other really cool things are fossils for the park, which are tree molds. They're trace fossils that are indication that life was there. And sometimes they make some really remarkable molds. So if you imagine the lava flow coming out slowly, creeping around a tree, not bowling it over, then you can end up with ones like this that's vertical. If you knock the tree over and the lava flows over it, you can end up with a horizontal lava tube like there as well, or here on the side. So we get both vertical and horizontal tree molds. We get things that were thrown out. And if you get a glob that was thrown out, it forms a crust. And that crust gets cracked by the gases internal to the glob as the gases expand. Then you get a cracked surface like a loaf of bread rising in the oven. Another one where the geologist gave a name that makes sense. So this is a bread crust bomb. If it gets twisted during its flight, and that's the dominant characteristic that you see, those are referred to as spindle bombs. If they're tiny and twisted, they're called ribbon bombs. And sometimes the glob can pinwheel and throw off rays. So this is a spindle, but it kind of looks more like, I don't know, peanut turtle candy. Some of the really big globs that don't have enough air time to solidify during flight go splat, like when a cow relieves itself. Hence the name cowpie. That's actually the geologic term for it. So, you know, this guy's about 4 feet across, and it went splat when it landed and flattened on impact. So that's a cowpie, but you can see it's got kind of this bread crust-like surface it had on it. This one here was more like a spindle, but that's about 12 feet long. And so sometimes you can have this big stringer thrown out that also goes splat. And but it's still a cowpie bomb. In this case, we called it the giant flying tube of toothpaste. And when it landed, then it squirted out some of the toothpaste, which is a little bit different texture to it, but this came out of this guy. So that was a giant flying tube of toothpaste that then squirted out some of the toothpaste when it landed. Sometimes when they land on a cinder cone, they embed, like you can see here and over here, and these little guys right there, pieces of cinder in the surface of the cowpie. And Scott Hughes, which some of you guys went with a couple weeks ago, he was out at the park the one time and I was showing him these, and he offered to pay the fine for having taken a rock if he could take it back for his classroom, but we said, well, not only would we have to fine you, but we'd have to confiscate it too. So that's the way it goes. Other kind of cool features, just like you have in a river. Mike took me down and we looked at your Army Corps of Engineers levee today along the Snake River. Well, Mother Nature makes levees without the Army Corps of Engineers. And so these are actually levees here on either side, and here's your lava river. So as stuff kind of gets spilled over the side, you can build up levees with lava flows, just like a river can build a natural levee or the Corps of Engineers can build a levee. Also, once you form a crust, and like freezing the water on a swimming pool, and you keep putting more water underneath that ice and you float it up, you end up with what's termed a pressure plateau. This is Tiffany again for scale. And so this surface got inflated all the way up to there, forming what's called a pressure plateau. A little less spectacular than here, but this is the same lava flow. This is the flow that came from this cone, which is called broken top, so it's called the broken top flow. And out closer to half cone is really well developed. And in here, it's probably roughly 10 feet or so high, something like that. So kind of a cool feature. Person here for scale, this is an inflation pit. This one we kind of used, those of you that are geologists, you know about a Jacob staff. We jaked up through the inflation pit, and there was actually 75 feet of relief from this inflation pit. So as the lava flows out, it may hit an old topographic high, kind of freeze around it, steps back. The next time there's a new surge or pulse to the lava, it'll rupture and inflate up, step back, rupture and inflate up. And so you have a whole series of these kind of step, step, step affair to it. Those are called inflation pits. The circulation, layers of bubbles, again represent surges or pulses down through the lava. So this is out going to the cave area. You walk right past this on the cave trail. And so that's one event, and you can see there's many, many events. If you take this area right here and look at it up close, you can see that when this layer came up, we had already a layer with lava stalactites that were hanging down, and they got bent in the direction of flow, which was that way. And then the new layer there, and then it continues on again and again and again. So many surges and pulses down through these tubes. When the flow gets almost stagnated, Mike and I were talking about this earlier today. This is a King's Bowl, and so when this thing was almost stagnant, not moving, it was still fluid enough that the gas bubbles said, "One out!" And so as these bubbles tried to work their way up to the surface, they kind of left these vertical streaks in the lava flow too. So that's something you can go and see. This is out near the vent area for the Wapai flow. And here I am paddling my lava canoe. I couldn't let Mike outdo me with having a boat. So this is my lava canoe. And it's the same kind of thing as you have as water comes off the mountains. You get alluvial fans. Well, think of the same thing in lava, and you end up with all these distributary channels just like you do with an alluvial fan. And sometimes they'll come together and they'll split again. So split, and that's how I got my canoe. But here you can see them coming down from the vent area. All these little tiny distributary channels. So that happens in lava too. Other features, flow ridges. This is a flow ridge at the Sawtooth Northwest flow. Tiffany again for scale, one of my GIPs. And kind of think of lava as a brownie mix. And you pour that brownie mix into your pan and it starts flowing away and you kind of get these little undulations to it. Well, each one of these flow ridges is kind of one of those undulations rolling away from where the vent was. We also get pit craters, which are collapses down into the major, this is along the major route that was followed by the lava that went 26 miles east as part of the Blue Dragon flow. And you can see those here. So here's the spatter cones where it came to the surface. Some collapses back into this major tube system. But we also had things like this, which was actually a lava pond. So a weak spot in the tube, the lava came out of the tube, formed the pond, and then at some point drained back in, kind of draping down the middle of this pond. And so it left a basin. Drives geologists nuts because this is called Little Sink, but a sink in volcanic geology means a rimless collapse. And it's not. This is a constructional feature. Okay, older areas surrounded by younger flows, whether they be very small or much larger, or in the case of some of them, several square miles. These are called Kipukas. In Hawaiian, basically, it kind of translates as meaning an island. So this older area surrounded by a younger flow. And these are of real interest to botanists because they can go out, because, you know, you think deer and elk are going to cross miles of lava to get to that? No, they're not stupid. And if you're a rancher, you're not going to be a rancher for long if you decide, well, I'm going to take my cattle out there. Okay. You think, how many of your cows do you think would survive getting out there? Probably zero, plus how would you get them water? So these represents areas that have had no grazing pressure, either from domestic use or from wildlife. And so they're a perfect place for biologists to go and see what an unaltered botanical environment would be like. We also get chunks that got floated off. Some of them, like this guy, you know, they're the size of a warehouse. Others are smaller. Here's a person for scale. So many different sizes, but we also get chunks of crater wall that with a, if remember, cinder cones are really highly gas charged. That's why the stuff got thrown out as much as 2,000 feet. So it's much, much less dense than the lava flows in general. So some of these crater walls get floated off like rafts, and so they're referred to as rafted blocks. We also get some really cool things. Mike, I know here, is a chemist, and one of the things that made Craters of the Moon so bizarre is it has a wide array of chemistries. And one of the reasons for this array of chemistries is it assimilated previously existing rocks. So in the case of this little guy here, and then a close-up of it, this is called a granulite, which is a high-grade metamorphic rock. These are believed to have come from a depth of about 26 miles. ergo a lower crustal rock. Ages on these guys, based on some of the zircons in them, come out anywhere from about 3.1 to 3.6 billion with a B years old. And they have altered some of the chemistries. Another thing is there's this young whippersnapper right here. Here you can see the basalt rim, and inside it, this is actually chalice volcanics. Over here in your neck of the woods, Stampsoricas are the same age. You know, young whippersnapper, 50 million with an M years old. But they too contributed to altering the chemistry as they got melted into some of the basalt mixes. And sometimes you get the froths, and these are kind of hibbly-hoys. We don't know what they are. They're not a girl, they're not a boy. They're a froth. And Lisa Morgan was looking at these, but before she retired, she never got the paper finished. And so we don't know the paternity of these guys yet. It could be chalice volcanics, it could be some of these, it could be some of the rhyolites from the track of the Hotspot. We don't know, but we got a bunch of these kind of pumiceous things that are out there in places too. Caves. We got about 7 different kinds of caves in the park. We'll just look at a couple of the main ones. Obvious one, lava tubes like Indian Tunnel, or a small lava tube here in the Broken Top Flow, or this is some stack tubes you can see in the Broken Top Flow, people there for scale. This is at the Buffalo Caves area. In the Great Drift itself, this is Bear's Den waterhole. And then we get some of these differential weathering ones. This one is really kind of cool because now we get into human history. Because if you look right there, do you see that little thing? That's a close-up of it. And it's a sunburst with 7 rays. And of course, if you're a Native American, there are 7 cardinal directions. Northeast, south, west, above, below, and within. Also sometimes, if you're New Ager, the now. But the Native Americans shared those same beliefs. If you stand next to the sunburst, and I've been there on the solstices and the equinoxes, there's a little dash right there by my radio. If you stand by this, line up with that, that is where the sun comes up on December 21st. And if you're a Native American, that's significant, because what does that mark? The rebirth of the Earth Mother. The days are now going to increase in length and get longer. And so it was something special. The cave is oriented north-south. In the south end is here. The north end, there's a small window you can see out. What is the road you walk in life? Your road you walk in life is the good red road. And it runs from south to north. The colors for the north are blue or white, and if you look out the hole at the end of this cave, you see the sky and the clouds. So a tremendous amount of potential significance if you're Native American, and that's kind of what makes geology fun. There's all these other stories that come into play. Inside the caves, you get things like, lava stalactites that hang down. You get some areas where it flowed at a level long enough it starts to kind of collect the flotsam and the jetson of the lava flow and build out these little curves or bathtub rings. And they can go together and make a new floor sometimes. You also get these little soda straw-like things that grow off the ends of some of them. And quite often, these have a submetallic appearance because when you remelt basalt, it doesn't have the gases dissolved in it any longer, and it takes on a submetallic appearance when it recrystallizes. And so both these guys, the kind of soda straw things, and this submetallic appearance is an indication of remelt. So, craters has been a place that has been studied for a long time. Native Americans were out on the eastern Snake River Plain and witnessed at least the last 4 or 5 volcanic eruptive periods. maybe all of them potentially. You know, we had earlier explorers that came to the park, and you know, here's a natural bridge. So if you have part of the lava tube collapse on both sides, the part that's left is a bridge. We had people like Edgar Mitchell, and for the 30th anniversary of them studying at the park, they came back out in '99, because '69 is when they studied at the park the first time. And Edgar Mitchell and Cernan and Engel all visited the park for the 30th anniversary. And then here's Tiffany in uniform, the GIP that worked for me one summer. And you know, so we've got young people studying and working on the geology yet today. NASA's finished up its 3rd year of a 5-year project in Craters of the Moon, so NASA's still working out there at the park. So it's been kind of a cool place. And if you come to visit, remember, leave only footprints, take only pictures or memories. And I blasted through that for you guys pretty quick. I kept it to right at an hour. I've never done that. I'd be glad to answer any questions if you have something you want to ask. Anybody? Yeah.
Yeah, Kipukas, the old lava.
The older area is surrounded by younger
Are
flows.
there any rodents out there? I was just curious if there's anything to see at all.
Yeah, there are things out there. There's certainly voles, gold mountain ground squirrels. There's some whopping big rattlesnakes, western rattlesnakes that eat the rodents. And of course, the rodents are there to eat plants. So yes, the answer is yes. Yeah.
What other reptiles are there?
Well, there's a number of snakes. There is the western rattlesnake. We do have a western racer, which is fast enough it can actually catch the mice as they're slithering. We do have garter snakes out there. We have the things that look like giant earthworms, the rubber boas. They're a cool snake out there. The most common one that visitors actually see is called a gopher snake, who sometimes will mimic a rattlesnake to try and fool you. Don't mess with me. That's probably the most common one, is the gopher snake. We do have a couple of lizards. There's a horned lizard that's out there at the park. We do have a couple of amphibians. Some are associated here where there's the limited water we have, but there's a couple of frogs there. And then there's a western skink, which you actually see along the cave trail. The juveniles have a very iridescent blue tail to them. So we do have western skinks also.
What's the biggest rattler you've ever seen?
Ooh, he was between 5 and 6 feet anyway. That was out at Kerry, Kipuka. And we just called him Grandpa because he'd greet you. It's like, oh, dude, this is my territory. Them is my roads. Don't you go eating in it. Okay, anybody else with a question? Well, I would say thanks for coming. If you want to order the map or the book from the Natural History Association, just take a picture of the order form and call a park, and they'll be happy to sell you one.
So before we break up and move the chairs on this side to that wall and the chairs on this side to this wall, I want to thank Doug for a small token of our appreciation for making.
Well, thank you.